Morning. How are you today? Okay. So today we will talk about very important topic of Kalman filter. And this is one of the most popular filters in many different domains. So this is not only important for controls, you have multiple other applications for that. But before we get there, I would like to mention a few technical things. So first of all of the homeworks were published. You have total 8 homeworks. All of them were published. I believe I published also probably solutions for 5 of them. And you need to complete your review if you haven't completed it yet for others' homeworks. So you have assignments to go through others' homeworks and to label them. And please do not leave only comment like it looks great, everything is fine, but make actual comments, okay, on things which do not match, because it's not very useful just to know that work is great, or a few mistakes are there, but we don't know where they are or what they are. It's more useful when you actually point into the actual problems, where there are differences between the solution, official solution, and given solution. Okay, is it clear what I'm saying? All right, so please complete all of these published homeworks that you have assignments on, and hopefully in a few weeks I will be able to give all of the grades for all of these homeworks. And my philosophy in this course, as in any other graduate course, that you're here to learn and not just to be graded or anything like that. So if you invest enough time and effort in doing the homeworks, it's much more important for me that you will try and you will get the right specific number answer to the question. So it's much more important for me that you will understand the theory and you will understand the procedure, how to get to the answer, and not particular calculation. Okay, so calculation is very useful, that you will just train your hand to solve all these exercises. Okay, that you'll have understanding of how computer does that, right? But if you got the process, particular numbers are not that important to me, at least. It will be a little bit different type of assignment for the project. So I'm grading projects in a different way. I'm more interested in how well you can report on it. So you are doing some particular work in your project, right? You're completing particular tasks. So you get particular analysis of the data that you get and gather from Simulink or MATLAB or whatever you run it in. The point is that you shouldn't show me results which make no sense. Again, numbers are less important, but if numbers make no sense, this is where it becomes very important. So pay attention not to numbers, but to meaning of the numbers, to insights. Obviously, if you put in stabilizing optimal controller, closing the loop, and system is diverging, this is not good, right? Regardless of what numbers you've got for UK. If they're close, not close, if you made some typo or whatever, you're stabilizing this optimal controller. Obviously, it needs to be stable and closed loop, right? So make it sensible, right? If it is not sensible, you can always come and ask questions. We will have probably like a lecture or two devoted to different questions on projects and other topics which you might miss or whatever. Okay, so the point is, don't afraid to ask questions. More questions you ask, more likely you to have higher grade on the project. Okay, and from my perspective, C for that type of course is failing grade. Okay, officially it's not, but in my mind it is, which means that you probably haven't asked enough questions and you haven't tried hard enough to get your stuff learned. Okay, so ask questions, please. I'm here to help. Okay, any questions on the homeworks, previous lectures? So we practically completed all of the optimal controller design using symmetrical root locus and Riccati equations. And now the plan is to move to optimal observers, which are also called Kalman filter. Any questions so far? All right, so what is the motivation for Kalman filter? Motivation is very simple. Same motivations that we had for observers. You have in a system, a normal, regular physical system, typically you have some states which are hidden states. And you might have heard about hidden states from other theories like machine learning or computer vision or some other places where you have hidden Markov models and other things of that kind. So you have hidden states. So what does it mean, hidden states? In our case, same thing as everywhere else. We just cannot measure them directly. We cannot have sensor on each single X. So you have states X1, 2, 3, 4, 5, 25. We can measure some of them, and this will be our output, but we cannot measure some others. So you cannot put sensor on every single state. You want to estimate it somehow based on your understanding of the model. So you're saying, well, if I can trust to some level my model, I will use that model to predict how the state will evolve in time without actually putting sensor and measuring it directly. Okay, so you want to guess it somehow. And that's exactly what observers do, right? You have particular model, you design particular gain L, and this gain will converge somehow to the real state eventually, not immediately, but eventually it will converge to the correct state. This is promised to us mathematically that we will get that. So Kalman filter is the same thing. It's trying to estimate hidden states, which you cannot measure directly. But here you have additional assumptions on what is going on to your system, okay? So assumption number one is that you do not know the model precisely. Yes, you have some idea about your matrices A, B, C, D, but they are kind of not exact. And this is natural for any systems, right? You cannot measure all of these parameters in the matrix A, for example. You cannot measure them exactly. And they also will change in time. They will fluctuate based on temperature changes or whatever other changes. And the system also is not exactly linear. So you have uncertainty in these parameters, in these values of the matrices that you have in your system, right? So how can you build your observer based on estimation, based on kind of unknown parameters or uncertain parameters? So you know them kind of, but not exactly. You know to some level with some tolerance. So what should you do? So this is exactly what Kalman filter helps you to understand, like what can you do if you assume something on the tolerances and also on the distribution of noises that you have in your system. So you have some limiting factors here. The assumptions are limiting to some extent, but they are pretty natural for most physical systems that we know of. Okay, we'll talk about these assumptions later. Also, you have all kinds of noises entering your system, right? And noise is by definition something unknown, right? So you cannot predict how the noise will look like. It will just enter your measurements. Your sensor will measure something plus noise or multiplied by noise or some other function of noise. And every single time you run the same system with exactly the same initial conditions, with exactly the same properties, the output will be measured a little bit differently. Okay, same system. Why? Because of noise. So noise, by noise, we define not only physical noise. And by physical noise, I mean the actual electromagnetic radiation and other things happening, hitting your system somehow from outside, radio waves, which are disturbing your system. I'm talking about our absence of knowledge or tolerance of the system or tolerance of the sensor. Okay, I also call it noise. In a sense, it is noise. It's just something that you do not know and cannot predict how it will change. You can assume something about properties of that thing. Maybe you can assume that it has like single mode. So it has like maximal mean value and then smaller probability of having some other values, okay? So it could be zero mean noise, as example. So on average, it will be zero, that noise. But it could be some other average as well, right? It could be all kinds of things. So you can assume something on noise, but you still don't know for each realization of the noise what number you will get. Like if you generate rand n function in MATLAB, it will every time throw you some new number. This number could be from minus infinity to plus infinity, practically speaking, any number. I mean, not exactly within the boundaries of ability of our computer to show numbers, but it could be any number. How probable it is to get 5 trillion? Not very likely. It's much more likely to get number 0.5 or close to it, somewhere in the range of 0.5 versus some numbers in the range of trillions, because Gaussian distribution looks like that, bell shape. So it's more likely to get it close to zero and less likely to get it farther away. But this is how natural noise is also distributed. This is random white noise will be distributed like Gaussian, the bell shape. Okay, there's less probability of having like really extreme values in your noise, but you still can have them. It's not zero probability, zero likelihood in that sense, because if you remember from probability theory, probability of getting number of 0.5 out of Gaussian distribution, what is that? Or let's run random number 1. What is the probability of getting number 1 from Gaussian distribution? And sigma is 1. It's like exactly it's 1 sigma. So what is the probability of getting that number 1?
Like 10 or 25%.
The area under the plot, it's 65% approximately.
Oh, including all previous values.
Yeah, so it's like less than 1, it's 65%, yes. So what is the probability of getting 1? Like 65% is like between -1 and 1. Yes. So what is the probability of getting 1?
Exactly.
Yes. This is probability 101. It is 0 as any other chosen number. Probability in continuous distribution, probability of getting any particular number is 0 always for any number. If you're saying like, what is probability in that Gaussian distribution to get exactly 1? The probability is 0. You cannot get it ever, technically, though you can get it, right? This is the probability issues. So you can always talk about ranges of numbers. So it might be like 1 plus minus 0.01. And then you have that area under the plot, which will be your probability of getting that thing. But if you are talking about the point on the Gaussian, which corresponds to 1, it's likelihood. What is likelihood of having number 1? This is the value of the distribution for number 1. And then you have particular value for that, which is exponent of minus x squared, exponent of -1. So you can actually compute it and divide it obviously by square root of 2 pi sigma squared. So it's divided by square root of 2 pi. Something like that for Gaussian distribution. But it doesn't matter. So my point is that we always have all of these noises in nature, and we need to take them into account because every time you'll be able to predict some particular states, noises will affect it. And before that, we never dealt with any noises. We said like all of the signals are clean. We are simulating everything in MATLAB. Everything is beautiful and nice and no problems at all. Okay. Now we have noises as well. So Kalman developed that filter, which is called on his name. And this is optimal linear observer. What does it mean, optimal linear observer? It means optimal means that minimizing some cost function. Okay. Optimizing on something. It's always optimal in some particular sense. So you never say optimal without meaning of what optimal means, because it's meaningless if you're not defining what you're optimizing on, because optimal for something might be not optimal at all for something else. So you need to be very aware of what you're optimizing for. And we will talk about what Kalman filter specifically is optimizing. And it's natural for observers to optimize that thing, and we already tried to do that for regular observers, but we haven't talked about optimization at the time. Okay. And this filter assumes that both uncertainty in your system, which is parameters of the A matrix and so on, and noise which is added to your measurement, both Gaussian distributions, which means that bell-like shape, which is practically 1 divided by square root of something, times exponent of minus something squared divided by some coefficient. Okay, but in that case, it might be multidimensional. So the Gaussian distribution will look a little bit differently. So it will have, instead of sigma, which is like divided by 2 sigma squared. If you remember, I don't remember, but maybe you remember all these formulas. So it was, I'm just guessing here, I guess. So it was 1 divided by square root of 2 pi sigma squared exponent of minus, it was probably like, let's use some other variable. So it would be t minus mu divided squared 2 sigma squared, something like that, if I remember correctly. Remember, this is Gaussian distribution for one-dimensional variable t. Okay? But if it is multidimensional, then the formula looks differently because this needs to be already with matrices. So it would be some other coefficient with some other root, and you will have some other coefficients here, whatever they are. It will be, I believe, exponent to the minus x transpose covariance matrix inverse, and then x, something like that, probably. So x will be vector, c will be matrix, not the same c that we are using for systems, it's just covariance matrix called inverse, something like that. So this is multi-dimensional Gaussian distribution, which might be the bell shape, but in multi-dimensional. It could go into multiple directions. It could look like ellipsoid in multiple dimensions or other shapes. So it doesn't have to be like circular level set. It could be any ellipsoidal level set. Okay, something of that kind. Don't cite me on that. It doesn't matter that much. The point is that noise could be also multidimensional, so the different noises at different states might be correlated, or maybe not, but they could be. So you might have entire covariance matrix which is not diagonal matrix. If the noises are uncorrelated, then the covariance matrix will be just diagonal matrix, and you will get to multiple states of that kind. So it's just multiplication of exponents of that kind, just in different directions. So you'll have like x1 here, x2, x3, x4, and multiple exponents multiply, they will be completely disjoint. Okay, but they also could be correlated somehow, noises in particular things. And Kalman filter assumes that you have just some particular covariance matrix here for these noises, which you can update in time. Okay, so you can actually measure and use it for updating the covariance matrix. I'm just trying to give you a brief overview of random signals and random systems, just that you'll have the terminology in your mind. Okay, covariance matrices, mean, which is average of particular values, and so on. And it is very popular in controls and very popular in tracking, visual tracking or regular tracking of different objects. So you can estimate their position, state, shape, whatever you want to estimate, okay? Very popular in computer vision. And also popular in machine learning, because there you also need to optimize different processes and get some hidden states. Because if you're thinking about neural networks, that's a very popular example in machine learning. They have a lot of hidden layers and hidden states for those layers, which you can estimate technically using that type of estimation techniques. Another good thing about that type of filter is that it's relatively easily, and when I'm talking about easy, I will mention that in a little bit, what easy means in that case, but relatively easily expandable to other cases, which means you can have extended Kalman filter, unscented Kalman filter, particle Kalman filter. You have probably a dozen more names for different types of Kalman filters, which we will not learn in this course. We will learn only classical Kalman filter in this course. But you have other versions which work for nonlinear systems, for different type of noises, for colored noises, for shifted noises, for all kind of, okay? And obviously you have all these extensions of regular Kalman filter based on the original Kalman filter. And Kalman published that thing in 1960, the first filter, and he had actually two publications. One publication on his own, and this is the filter that we'll be learning today. And actually, I believe even in 59, maybe he published the previous publication with Pussy. He was his PhD mentor. And this was Kalman filter for continuous time systems. Kalman filter, as we know it now, it's for discrete time systems only. But you have also a version for continuous time systems, which is Kalman-Busse filter. All right, we will talk about that next lecture when we'll talk about linear quadratic Gaussian control, probably next week. But today we will talk only about Kalman filter, which is for discrete systems only. All right, and he had a lot of troubles publishing that thing, and that's why I'm talking about easy, a little bit in quotes. Okay, so now when we know how it works, we have like 10 different proofs of Kalman filter formulas, and people understood it in like tried to solve it in million of different ways, applied that to probably hundreds of thousands of applications. And if you just Google Scholar, put Kalman filter, it will throw you like 100,000 citations on that thing. So people use it for everything and everywhere, for a million of different purposes. So now we understand it very well. So for us, we just got used to it in a sense, in terms of math and formulas, but it's not that easy. The problems that Kalman was solving is extremely difficult mathematically, okay? And even the fact that he found this solution is magical in a way, that it was possible even to solve the problem in the first place, even for that simplistic linear time invariant case, okay? It's still super difficult. And his paper, I believe, was rejected twice by IEEE. At that time, it was not IEEE, it was some other name, but before IEEE, same organization became IEEE later. But in 60, it was something else, and they rejected in good journals, good controls journals, where he tried to publish these papers. They rejected it because they couldn't understand it at all. It was like pure math. I saw the original paper. The original paper looks like no text, just formulas. Okay, all paper is like 10 pages of formulas, just like that. And he, I believe, published that in some. So he got kind of really upset about that, and he hated the organization for a while. And he sent it to some Mexican journal, which was not known to anyone, something automatic. And this journal is famous now for his paper. This is the paper in this journal. Okay, so well, this is just hint for your futuristic studies and your papers that you're publishing. Don't get too discouraged by being rejected. Okay, Kalman was rejected multiple times with his papers, and now it's like hundreds of thousands of people using it everywhere for everything. Okay, so what is actually the minimization process that he is trying to give you? Okay, so what is the actual question that he's trying to solve? This question is very reasonable for our case. So we want to estimate state X. So we want that X hat, right? And you cannot measure X directly, but you can measure Y directly. The purpose of that thing is to estimate X hat. So what would be the reasonable way to do that? You want to minimize the distance between the real X and estimated X. So what should you do? Do absolute difference between them and squared for making it differentiable, because you want to optimize. In optimization, typically you're making squared error instead of regular error. Why? Because squared error is differentiable. And for optimization, you need derivative with regard to some variable equal to 0. This is Fermat theorem, which says that it is flat when the derivative is 0, right? This is maximum and minimum point. Extreme points are always where the derivative is 0. But if the function is not differentiable, then how would you know, right? It's difficult numerically also. So we assume differentiability of the function, and for that we are using cost function, which is square of something. Same thing we use for LQR, right? we used like u square plus y square, that kind of thing. Or x transpose qx, which is also quadratic form, instead of using square root of that. All right. Same thing here. We are minimizing mean square error between estimated x by Kalman filter and real x. And we call that E, if you remember, for the observers. And interestingly, Leuenberger, who developed regular observers, published that probably like 4 or 5 years later after Kalman, which means that Kalman already solved the problem with noises, with all the other things coming in, uncertainties in the model, like he solved the problem. And then after probably the publication was, I believe, in maybe 64, 65 by Leuenberger, okay? Leuenberger came and said, well, let's ignore all the noises, let's ignore all the other uncertainties in the model. For perfect model, this is the observers that you need to design, okay? So it was technically much easier problem to solve, which was already solved in a way. But it was interesting angle on that, and I don't think that he even knew about Kalman's work or relation to his observers. Because Kalman even never mentioned observers. He talked about estimation and talked about filters in the first place. He never mentioned the word observer, okay? Observer word was developed by Leuenberger 5 years later. But this was same formula as Kalman used for his filter. So probably Leuenberger didn't know about the existence of that filter. At that time, as you know, no internet, no communication, like all you could find is actually order the journal, paper, journal, and read it. This is the only way to learn something. Okay? Sometimes you can get it in the library, but not always. Okay, so let's formulate it mathematically. Let's formulate the problem, and let's see the solution to that problem. So here's the problem that we are trying to solve. Our new system is discrete time, as I mentioned. So xk plus 1, you have axk plus buk. This is, as we used to see, a regular system, ideal system without noises or uncertainties. And I'm designing the uncertainty using particular noise, which I call wk. So wk, at each point of time, at each index of time k, you will have particular sample of noise. It could be some sort of positive or negative number taken out of particular distribution, and this distribution will be normal distribution or Gaussian distribution, white noise with zero mean. Okay, this is my assumption on the noise and on the tolerance, which means that let's say you ignore all of the BUK, okay? So this will be AXK plus G, which is also some matrix, constant matrix, times some noise. Practically speaking, this means that coefficients of the matrix A will change somehow, but on average, they will not, which means if you have zero mean, this means that your coefficients are not changing on average, but they can fluctuate. And bigger the standard deviation is or variance of that noise is, more they fluctuate. So more uncertainty you have in your parameters that you estimated for the matrix A. Right? And all the parameters in matrix A are estimated from particular system. Right? You estimated this parameter, so you know them to particular tolerance, right? But you do not know them exactly. But you assume that you know the average exactly, okay? So the average will be the average you put in the matrix A. And this noise will tell you how far away it could be from that average. And this weight matrix G will tell you which element of the matrix A will be with that particular tolerance, okay? So you'll be able to control like what you know about the matrix A and how reliable particular values in the matrix A. Typically, in all practical problems that I know of, it's difficult to choose the right G and the right type of noise. You can estimate the value of your noise uncertainty in your system, like how fluctuating the parameters in the system are, by just running multiple experiments on the system, and each time you estimate matrix A, each time you get a little bit different A, okay? Even if the system is stationary and everything is working well, you still have all kinds of noises, disturbances, stuff like that. So you get different A's. So you're making average of A's, this is your model, right? This is how you design it. But then you can see also distribution of values of A, and this will give you approximately the value of the tolerance or sigma of that noise W. Okay, standard deviation of that noise. This is how you look at it. But again, these are parameters that you need to play with to get good results with your particular system. This is the point of that formulation. Okay. Now, I will define that noise more specifically here, more formally. But this is just Gaussian noise with particular sigma and zero mean, normally distributed. So output Y, the regular system would be C times X of K plus du, but we can ignore that part. Now I add noise to it. So Vk will be noise of the measurement. So this is called systems noise. This is noise of the system or tolerance of the system, if you wish, tolerance of the parameters of the system. And this is measurement noise, which means tolerance of your sensor, technically speaking. How close your sensor measurement to the real measurement, the true measurement, okay? And all sensors, they have their own tolerance. More expensive sensors have narrower sigma, which means they measure very precisely, okay? Cheaper sensors are not very precise, so they could be very variable in their measurement of the same thing, okay? This is the idea. We also will assume that the initial state is distributed normally with particular mean and particular covariance matrix. Since this is a vector, it needs to have covariance matrix, right? To describe that n-dimensional distribution of the initial states. We will assume that it's also normally distributed. This is assumptions of Kalman filter. You can relax some of them, and then you'll have other types of Kalman filters. But classical Kalman filter assumes Gaussian on the noise of the system, Gaussian on the noise of the measurement sensor, and Gaussian on the initial state. Like everything looks like bell shape, but in n dimensions. All right, questions so far? Okay, so we have systems noise, we have measurement noise. Now we will define what they are. So what is that symbol E here, the capital E? So this is expectation. So what is expectation? Value. How is it defined? It's also called first moment, right? Probabilistic model. In probabilistic modeling, you have first moment, second moment, third moment, and so on. So what is that expectation say? So you have some random variable, WK, and each time you're trying to run that rand n command in MATLAB, it will give you a different number, right? So what is expected value for that random variable? Do you know function rand n in MATLAB? Like you ran that function, it gives you some number. Sometimes positive, sometimes negative. And rand n will have standard deviation of 1 by definition. If you want higher standard deviation, you just multiply by that number, the function rand n. Okay, like 5 times rand n will have you Gaussian distribution with the 5 sigma instead of 1. So what is the expected value if you run that experiment 1 million times? So you run loop from 1 to 1 million, generating numbers rand n. What would be the expected value as a result of that loop? This is normal standard Gaussian distribution, yes. So what is the expected value for normal Gaussian distribution of that kind? You have answer here, by the way. It is 0. It's mean value. Expected value is just mean, average of all numbers. So if you're running 1 million Gaussian numbers out of Gaussian distribution, on average, you will get 0. And more numbers you get, closer to 0 you will get. Like at infinity, it will be exactly 0. Okay, if you generate infinite number of numbers out of the Gaussian distribution. Why? Because it has mean 0. So you'll have some positive numbers, some negative numbers, they will cancel out automatically. So expected value, which is the average value, will be 0. This is what it means. Okay, what value you expect on average to get from a particular distribution. And this will be 0, expected value. And this is what it says. So expected value of that noise is 0, which means on average it will be 0. Same thing with the second noise. On average, it will be 0. Now, the expected value of WK times WN, which is cross covariance, it's technically speaking covariance matrix, we will call it W. Okay. Now, the other matrix for the second noise covariance matrix will be V. These are just names. I'm just giving particular names for this covariance matrices of measurement noise and of systems noise. All right. And these noises will be independently distributed. So the noise VK will not have anything correlated to WK. They are not correlated at all. Okay, these assumptions of the model. And this means that the expected value of their multiplication will be 0. Okay, they are not correlated in any way for any K and M. Any questions so far? So this is how we define the noises. Now let's see what it means in terms of system modeling. Okay, it's very important to understand. I'm going slowly just for you to understand intuition behind all of these things that we are working through, because the math will be tough. I will just give you a bunch of formulas and you will need to apply them somehow. But I want you to understand the meaning of these formulas and where they come from and why it's important to play with this number, like to play with these numbers and these models and these weights and whatever you need. You need to have intuition behind it a little bit. You need to feel which way you need to move numbers to get particular outcomes. So here's the thing. Let's see what is the meaning of W and V, which are those covariance matrices in a sense. Think about that as standard deviations of V and standard deviations of W, because these are on the main diagonal of these matrices. These are standard deviations or variances in that sense, standard deviation squared. So what does it mean to have broader standard deviation or variance of distribution? What does it mean in terms of signals? It means that you have higher uncertainty in the numbers that you will get. So they could be far away here or far away there. But if you have very narrow sigma standard deviation, means most likely they will be somewhere here. They will not be there, or very super unlikely to be there, very likely to be here. So broader the standard deviation is, or variance, less knowledge you have about your system or your noise. It becomes more uncertain, right? This is the meaning of higher variance. So it could be all kinds of things instead of particular things. So if you have low W, which means you have very narrow deviation on that noise, you need to trust the model. So your model is very precise, actually. Okay. So this means that if your W is very close to 0, which means very small standard deviation, right, on each one of the states, it's almost 0 part, right? So you're multiplying it practically to 0 and you get ideal system, almost ideal system, right? But if standard deviation here is very high, very broad, then it means you don't really know the matrices A and B. They're not very precise. They could be all kind of, right? So your model is not really reliable. So you shouldn't trust the model. You should trust more the measurement. Same thing with V, but the other way around. So let's say if V is very narrow, which means that the output that you measure, Y of K, is almost for 0 here. V equals almost 0. It's like very, very narrow, very close to 0, which means that your measurement is almost exact. or precise. And this means that you can trust the measurement more than you can trust the model. And it's always balance. So all these filters is like how you balance your trust in the model versus in ideal model versus your trust in your measurement. Both of them have some sort of noise. Both of them are not 100% exact. Otherwise, you will just use regular observer, but you can't because you have noise, right? But here you have compromise between whom you trust more. Do you trust more your models that you estimated, or do you trust more your measurements that you measured with your sensor? And if you have like super expensive sensor, which is very precise and accurate on everything, then just trust this part. Otherwise, trust your model, okay? This is the overall idea. Now, this is a problem that we are trying to solve. We are trying to estimate state X from noisy measurements YK as a regular observer to minimize mean square error. So what mean square error? Our error between the states is xk, which is the actual real state, which you cannot see, it's hidden from you, okay? Minus x estimated by Kalman filter. You want to minimize that thing. We'll get to that. So covariance matrix of the error, I will define that as P of K, okay? It's just, all these are definitions, how I call them. So P of K is the expected value of EK times EK transpose. So what are the dimensions of that thing? So EK is vector like that, and the second vector is like that. So what would be like n by 1 and 1 by n? So what would be the multiplication? It would be matrix n by n. And this is practically covariance definition of covariance matrix for this error vectors. This is covariance matrix. That's exactly what it is. If you remember something from the statistics course, or probability or something like that. Okay, so that's exactly how covariance matrix is defined. It's average on all of the possible distributions of the possible realizations of the error vectors E. Okay, and error vectors are defined like that. But if you invert that thing, which means you're taking E transpose, which would be row vector times column vector, it will be a number. It's like dot product, right? Then you get single number here. And this is the number that you want to minimize. This is exactly what MSE is, mean squared error. It's like every element of that vector squared and summed on all of them, right? It's like E1 times E1 plus E2 times E2 plus E3 times E3 and so on. This is what that thing is. And take average on all of these possible realizations. You want to minimize that mean of squared error. This is squared error practically, right? Do you understand what I'm saying? So you're minimizing that. This is error of variance. And you want to minimize that. This is what Kalman filter is doing. Minimizing the squared error like that. But all of its possible realizations for all kind of realizations of noise. Okay? So it is doing that on average. So each particular realization might not be exact. Like you will not get the best possible result for each particular realization of noise. But on average, you will get it optimal. Okay, this is the best you could do out of all possibilities. All right? This is our solution, Kalman filter. And let's see another way to look at the intuition behind Kalman filter. There is a very good paper, more than 10 years ago. It's published in IEEE Signal Processing magazine. And I strongly recommend reading that paper. It's called Understanding the Basis of the Kalman Filter via Simpling and Intuitive Derivation. So they actually prove Kalman filter for that particular case that they show. And it's relatively easy. Yes, it's maybe not super easy, but if you're interested to see like where these formulas are coming from and why it is making any sense, you should read the paper. We will not do proof in the class for Kalman filter. All right. But it's kind of nice and colorful and beautiful magazine paper to read. Okay. You can download it. We have subscription to that journal, so you can see. But let's see intuitively what Kalman filter is actually doing. Like, what is the idea behind Kalman filter? Overall idea, okay? Why it needs Gaussian assumptions and all of that stuff, okay? So let's pick some simple problem. And this simple problem is cart on the track. And you have measurement of distance sensor, whatever, infrared or ultrasound, whatever. You have some sensor which is obviously having some tolerance, so that measurement distance is noisy. So you don't know exactly the distance to the plate here on the cart. All right, so far. So this cart is standing here, and it starts to move to the right at particular speed. Okay, so it's just starting to move, and you keep measurement at particular time points. Time points are samples, so system is discrete time, which means you're pinging, sending signal, return back, measure the distance. Sending again, measuring back, get new distance. So you have these points of the distance which are distributed, and they have some noise of the measurement. So it's not exact distance that you have at that particular moment of time, but distance plus minus tolerance. Okay. We assume that the initial location is also not exactly known because the only way to know it is actually to measure the distance. And your measurement is not exactly precise, okay? So you have some distribution of the state. So the card, on average, most likely, the highest likelihood is to be at that point, but it might have been here or there based on your initial measurement of the card location before it started to move. Okay, so it's somewhere distributed in that region. So you have that Gaussian. Now, let's say the card starts moving, and you have model of its movement, which means you have the dynamic model which is saying to you like where the card will be at your next time point, okay, at k plus 1. So you have that a times previous vector of location, all right? Now, again, this model is not exactly right, but it has some tolerance. What would you assume your uncertainty about your system will become if you're just propagating it without any measurement? So you're kind of closing your eyes, you do not see how it moves, and you count in 1 second, and your model says that within 1 second, it should be on average here, okay? So what is your uncertainty, going up or down in terms of compared to initial state? So is your uncertainty higher than initial state or lower than initial state? So you do not see where it moves, how it moves, what it does. So obviously your uncertainty is going higher, which is designed by the system to provide broader Gaussian uncertainty, okay? So before you measure anything, and you don't know where that thing is, right? But you are using your model just to predict where that thing is. Because you are doing xk plus 1 equals ax plus bu, the previous x. So you know the previous x, which is on average here, right? So you're taking that average x, you're plugging it into your system, which is a times the previous x0, plus b times u that you know u, right? You give u, so you know u. But you are plugging that equation, but you don't know what the noise is. So you don't know the part of the GW. So assuming I will take only the original part without GW, okay? So my predicted value without measurement will be that AX plus BU. This is the best I could do. I don't have any additional information about the system, right? That's all I have. So after that, my uncertainty about location will be obviously much broader. So it could be here, it could be there, it could be in all kinds of places, depends, okay? Because my model also is uncertain, so my matrix A is not exactly right, okay? It's approximately right, but not exactly right. But I will get that particular average with broader distribution. Now, at that moment, I ping the signal and get back the measurement, which means my sensor says, on average, it should be here, but my sensor has some tolerance, right? Which means my sensor will say, well, it's up to the tolerance of sigma here. And this is sigma of the V signal, right? V noise. This is a darker Gaussian here, okay? So that part says, if I ignore the model completely, and I don't know why the model where it's supposed to be, okay, I will just use the measurement. Measurement says it's here. but I have also tolerance, so it's here up to the tolerance, okay? And this is what the Gaussian is showing you, right? So what would be your best guess for where the card really is, given these two Gaussians, given these two uncertainties? So you have one uncertainty, another uncertainty, okay? Now you need to combine them together, somehow knowledge from both of them, from model and from measurement, to get your best guess. Like where the card is, what would be your top guess? And this would be that green thing, okay? So if this thing is very, 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 very narrow, where would you choose it? Super close to that thing, because your uncertainty here is like super narrow. If this orange thing is super narrow, probably you will choose it closer to the model. This is exactly the compromise between trust in the model versus trust in the measurement, right? But you can guess it automatically. You guess it just by multiplying two Gaussians. You multiply two probabilities and you get overall a posteriori probability. This is how you compute a posteriori probability. You're multiplying each probability by the other probability. So you multiply these two Gaussians and you get the green one. It automatically will happen if one of them is super narrow and you multiply it by anything, it will still look like that narrow thing, okay? But if both of them are broad, it will give you some Gaussian somewhere in the middle, most likely. So if they look like that, right, one will look like that, and another will look, let's say, like that. The multiplication obviously will look like that, right? So you have this will be something like that. Maybe it's a little bit higher here, but mostly following that thing, right? But if you have another case which is looking like that, we have one broad one, another broad one, the multiplication will look like that. So it will be probably 0 already starting here, 0 starting there, and then it will be probably something like that. Okay, when you multiply these two Gaussians. And this is exactly what you would expect it to be. So if you believe them equally, which means the uncertainty of each one of them is more or less equal, so you trust them equally, measurement and model, right? And one says the card is here, one says the card is here. And you cannot choose which one to believe more. You believe them equally. Probably you would just average them, right? You would say it's like between them somewhere. This is most likely place. And this is exactly what this red Gaussian will tell you. This multiplication of these two. So the highest point will be that multiplication of them in the middle here, because both of them are not close to 0 at that moment. All right. More than that, we have pretty simple theorem, which is stating that multiplication of any two Gaussians is Gaussian. So you multiply two Gaussians, you always get Gaussian. All right, which is very convenient property. This one will be technically narrower than each one of them, the multiplication, which means when you combine them together, your uncertainty will go down. So you'll get more precise location of the card in terms of probability, more likely location of the card. And this will be exactly the output of the Kalman filter. Like that location of the green thing, it will give you that value, which is most likely value out of both measurement and model. All right, this is the overall idea. This estimated location. It also will provide you that breadth of the green Gaussian. So this will be that covariance matrix that you receive as part of Kalman filter computation. So you will know how much uncertainty you have in your result as well, in addition to the mean value. So you'll have mean value, which will tell you like where's the most likely place for your card to be, but also how certain you are about its location. So it will give you also covariance matrix, which is very convenient side product. All right. Any questions on the intuition behind Kalman filter? Okay, and here's the theorem, the actual thing. And we will start with full version of it, which is not recursive version. Kalman's version was actually a recursive solution to that problem, but now we solve the direct solution, not recursive solution. We will have this problem, as you remember, is dual to LQR. Observers are dual problems to controllers. Same thing here. We will have some Riccati equation. Solution of that Riccati equation will be optimal for solving that particular problem. Okay. And as before, when you're doing conversion between controllers to observers, all you need to do is to convert A into A transpose, B into C transpose, C into B transpose. You're just renaming matrices with different names, and you get exactly the same solution as LQR, technically, for discrete case, right? But we will skip all of that. I will give you the actual solution, but the theorems look very similar to LQR, technically. So the condition for minimal variance asymptotically stable filter would be that pair A and C is detectable. If you remember, for LQR, it was A and B stabilizable, but here A and C is detectable. And V is positive definite and exists matrix H, such as that H is square root of W, and A GH matrix should be stabilizable. This is the theorem for uniqueness, okay, of the optimal solution for Kalman filter. And typically, these conditions are true for most systems. In that case, if this condition is true, the optimal observer or Kalman filter will be given by Z gain. Again, some sort of multiplication of different matrices. And P matrix is a matrix that we need to find, that covariance matrix, okay? So P will be solution of that algebraic Riccati equation, very similar to what we saw before for LQR, just with replacement of all kinds of variables with other variables, but very similar. This is discrete time Riccati equation that you need to solve to find the solution P from the Riccati equation, solving system of quadratic equations, putting it here, and you get L. And then in that case, your estimated K, X of K, will be written like that. So pay attention that you can write that same thing differently. So it's I times that thing, which is regular observer function, minus LC multiplied by all of Z plus LYK. So L could come out of the parentheses in a way, okay? So it's L times, practically speaking, differences between Y's. Y minus Y estimated. This is what you have here, which is exactly the formula of observer that we had before. If you remember, like estimated X was the original AX plus BU plus L times Y minus Y estimated or something like that. Okay. This is same approach, okay? But in Kalman, you have even more than that. You have alternative solution. And we will see why you need alternative solution in the first place. You just can write the same Riccati equation solution in a different way. A little bit easier to compute, technically. So you will need to define new matrix M, and you'll define it like that. And then you'll use that to solve the Riccati equation here. So P will be kind of simpler writing for the P matrix, but it's completely equivalent to the previous one. But pay attention that this Riccati equation is not the same Riccati equation as before. It's different Riccati equation, and this is why this solution is different. So compared to this one, you see that solution to the vector L, and this solution to the vector L. This seems to be much easier. So this is different matrix P, not the same matrix P like here in that thing. It's different solution, but you will get the same L. So the gain will be the same gain, but Riccati solution will be different. And so many times this one is more convenient type of way of solving. So in that case, you do not need to invert something. So in that thing, you invert in that thing, and in that thing you invert in only V. And V is positive definite, so you can actually invert it always. It's very easy to do, much easier. All right. Any questions so far on the?
Okay, can you go back to the one?
Mhm. Okay. So this is not recursive solution yet. This is actual solution of optimal observer, but solution can change in time as well. right? You might have solution which is converging to optimal solution with time. So the overall idea and difficulty, like this part is actually relatively easy to show. It's similar to LQR type of process where we are showing that optimality. But recursive solution is pretty complex and complicated. You want to solve the Riccati equation, but in time, which means for every single point of time, you want to find the optimal solution to that thing, all right? And the idea is that all of these matrices like P will be functions of time, or index K in that sense, okay? All of them. And you want to solve it without knowing the entire signal, because for the previous solution, you need the entire time points signal, okay? All the time points. Here I'm saying, oh, I have it up to time t, so I want to do that in real time, really. So I want to run that Kalman filter as a physical system in real time, so I do not know the future. I don't know how the inputs and outputs will change in the future. I want to do that in time. So how would I solve that thing in time? This is kind of complicated problem. And it's interesting that it has solution. And just a few definitions. So when I will use variables with plus or minus, what I mean by that, minus is before measurement and plus is after measurement. Okay, so this will be superscript. Okay, superscript plus means after I have the measurement, which is a posteriori, and minus is before the measurement. Okay, before I have any measurement for that time point k. All right. Also, I need to assume something on like what happened before zero time, because since the solution is recursive, I need to start somewhere. I need to start at the point of -1 time, like k equals to -1, pre-zero, right? Pre-zero state when I actually know what x0 is, how it is distributed, and things of that kind. So I would assume nothing for y -1, but then I will also need to assume something on x0, and I will use the distribution that we used before. So I can use just 0 or some other number. This is just to make these formulas work. Okay, I need to start somewhere. And this is how the formulas look like. These are Kalman filter solution. This is Kalman filter solution. And this is how it looks like. So x0 minus, which is before the first measurement that I have, estimated. I will just generate it randomly from the initial distribution that I have from x0. Or I can take mean value or measured value or whatever other value. This is just initial state, okay? So I will guess it somehow from the distribution. Sometimes you can do that. Sometimes you just choose 0 for everything. So and starting with 0 point. Okay, if you do not have any additional information about your physical system, where it's supposed to start. And also, I will need to start with some particular covariance matrix. Covariance matrix is n by n. Typically, you choose a diagonal matrix because you do not think typically about cross correlations between the noises on different states. And you're saying they are probably independent. But you can have some additional knowledge about your system. And if you have some knowledge about correlations between different signals, noises in your system, then you can use it somehow in your matrix, or you can estimate it somehow. But typically you choose a diagonal matrix of n by n, like zeros everywhere except main diagonal, and you start with particular numbers on the main diagonal. So you can choose it I, for example, identity matrix. All right, so this is your initial matrix. It will change in time. So Kalman will tell you how to modify that matrix. Closer that matrix to the real matrix, covariance matrix you choose, faster it will converge, obviously. But it will converge from any positive definite matrix, okay? This is good thing about it. But again, sometimes you need it faster, so choose your matrix wisely. This is, I'm talking about your project. Don't even remember in that project you have Kalman. Probably you should have Kalman. All right. So we will divide the Kalman filter into 2 different steps. First step will be measurement update. For any k larger or equal to 0, okay, starting with 0. So k equals 0, 1, 2, 3, 4, 5, and so on, okay? We want to convert p k minus, starting with p0 minus and x0 minus, into the same thing with plus. which means before measurement versus after measurement. Okay, so you are modifying X and P, which is state, estimated state, and covariance matrix before measurements to a posteriori one, which is after measurement. All right, so far. So this is what these formulas are doing recursively. So I'm defining new variable, and well, kind of unfortunately for us, Kalman's name starts with K, so people are using for gain K and not L variables in all those places, because in observers we used L for gain, the actual gain. And in Kalman filters everywhere you will see K used for everything because of Kalman gain. All right, so you need to remember that these are kind of similar, not the same, but similar things, just different name. Okay, so Kalman gain at time K, which is auxiliary variable that will be used later for computations, is defined by these formulas. And pay attention that everything in this formula is defined before. So K equals to 0 at the beginning, right? So P0 minus is given here. P0 minus is given here. All of this is constant. Like V is constant, is variance matrix, covariance matrix of the noise V. And C is matrix of your system C. It's like output matrix, it's C times X. Remember, like Y equals CX. So this is that C, your system, the system C. So all of that is given. For the second one, everything is given as well. So this one is X0 minus, which you get from here, which is your initial state, plus K of K, which you computed here. So it's already computed for 0. And then you have Y of K, which is measurement at time 0, initial measurements that you have. Okay. And then you have it. C is matrix of the system, and X0 minus also given. So all of these variables are given from the previous cycle, previous loop. Same with K plus, which is covariance, new updated covariance matrix after the measurement, which will be PK minus, which you can take from here, minus KK, which you computed here. C is given, PK minus, same thing like here, right? So all of this is given, so you can compute these three values. Now I want to get from these three values to the next time step, which means the next prediction. So you have prediction, measurement, prediction, measurement, prediction, measurement for each sample which is coming into your system. So now I had like new measurement. I use that new measurement to get these three variables. Now I'm using these three variables to predict the next location. All right. So next location will be that minus part, but K plus 1, right? Because it's next step. So the gain LK will be A times Kalman K, which I computed here, so it's known. XK plus 1 minus will be AXK plus, which I computed here. Okay, so it's known from the previous part. Plus BUK. UK is known because you are giving UK, you're providing UK. And covariance matrix minus equals A times I minus K of K, which is computed in previous step, times C times PK minus, which is computed in previous step as well. Okay, it's here. And then A transpose plus G, which is constant matrix from your system, times W times G transpose, which is also constant matrix. Right, so everything is given. And then you go back and continue from here. And you're doing that in the loop. Okay, you're doing that loop. For loop. For each measurement, you will start with that loop. And eventually you will just compute that LK, which is your Kalman gain, for your observer. Right, so this observer will be time dependent. It will be changing in time. And what we want to show is practically that this will converge to the optimal L, which is minimizing that mean square error of the states. And this is how it looks like. It's called steady state Kalman filter, which is for time goes to infinity, right? This P infinity, which is covariance matrix at infinity, will be that limit of the computed in recursive step matrix where K goes to infinity. And in steady state, all you will have, it will converge. So this is what convergence means, right? Which means previous covariance matrix will be equal to the next covariance matrix. And then it will stay forever, obviously the same covariance matrix, right? It will converge, is what it means. Now, steady state gain will be something which that K of K converging to. And L infinity also will be just multiplied by A. And the steady state Kalman filter is stable only if and only if the eigenvalues of that matrix are inside the unit circle, which means they are stable for discrete time case. Okay, so you can check if the eigenvalues of that thing are stable, and then your Kalman filter in steady state will be stable, not diverging, which is nice property. Any questions on the formulaic part? Okay, just to mention a few comments related to these formulas. If your noise is not Gaussian, not bell-like shape, but something else, some sort of colored noise, this formula still will implement linear optimal filter. This is the best linear optimal filter that you could get for your system. All right? It means that no matter what other filter you will be using, your results will be worse, even for other type of noises. Okay? The only thing which could you, if you want to improve over the results of Kalman filter, the only way to get it is to make a non-linear filter. Okay, which will be much more complex to analyze. Okay, this is complex to analyze, but non-linear filters are much more complex to analyze. But this is your only way to get results better. Okay, if you want it with non-Gaussian noises. All right. The algorithm works also for time variant systems, which means I don't have to assume in that case that matrices A, B, C, D are constant matrices, or matrices V and W are constant matrices. Like your noises might change in time, their like statistical properties, variances might change in time, and your matrices A, B, C, D might change in time, the way you want them to be. So it's linear by time variant system. Now, you will still have Kalman filter being optimal filter for these systems as well. All right, which is very, very, very nice property that your system can change in time, and your Kalman will change in time with the system together, and every step it will compute optimal observer for your time variant system. Right, very nice. More than that, from the computational perspective, if you want to implement that on real-time systems like embedded controllers or like actual real-time Kalman filter for your system that you want to work in real time in some hardware of some kind, okay? You can do that because you can compute all of the matrices P offline. If you're paying attention to that list of formulas, P is not dependent on practically no K, like K and P are not dependent on X at all. Okay, so they are changing by themselves somehow, okay? So this is kind of completely separate loop for K and P. They dependent only on themselves. So you don't need to know what your X is for particular P and K for a particular K. So you can compute them practically ahead of time if you know your matrices, right? V matrix, W matrix, A, B, C, D matrices. So if you know these matrices, you don't need to know what your state is, what your X0 is, what your, all the other things which are happening to the system. You can compute them offline. And this will make the system super fast. Now, for LTI systems, we will still get LK dependent on the time. So this means that initial conditions do not fit into the steady state. It's possible to show that some restrictions, with some restrictions, I mean, it's limited, not always, but pk minus will go to p infinity minus, which means it will converge. This k goes to infinity, and L will also converge as well. So that type of filter, where you have that kind of convergence, is called stationary Kalman filter, just terminology. What else? Yeah, and you have also all kind of problems with different textbooks. They call different variables with different names. So for you to be familiar, sometimes matrices W and V are called QW and RV, or sometimes even Q and R, similar to LQR. So they use the same variables for LQR and Kalman filter, Q and R, to define different variances or covariance matrices for noises. Okay, similar to your J definition. If you remember, J definition for LQR was with Q and R. So R was multiplying U squared, and Q was inside the X transpose QX quadratic form, right? So people are using that for Kalman filter, same letters in some textbooks. So if you will see that type of terminology, you need to know that these are the same thing. Okay. Any questions? All right, we'll continue next time, and thank you.